Good afternoon, everyone. My name is Kimberly Huguenard. I am an associate professor in the Civil and Environmental Engineering Department here at the University of Maine. And I'm going to be moderating this session on transportation resiliency and the impact to our infrastructure. So the session's going to begin with three 15-minute presentations, and we're going to wait until those are all completed, and then we're going to have a Q&A session for you guys to ask some questions. So our first presenter is Kirk Bosma, and he is going to be talking to us about probabilistic modeling under climate change conditions, compound pluvial, fluvial, and coastal flood risk. He is a senior coastal engineer and vice president at the Woods Hole Group. He earned his master's in coastal engineering from the University of Delaware in 1996 and his bachelor's of science in civil engineering in 1994. He has more than 25 years of experience in the fields of coastal sciences and engineering, as well as climate change, resilient design, specializing in the areas of developing gray, green, and hybrid coastal engineering adaptations for fostering urban and rural resiliency in a cost-effective approach. He has completed comprehensive coastal flood risk assessments that incorporate storm surge risk coupled with increased precipitation and sea level rise. So Kirk's work on the Mass DOT's Massachusetts Coast Flood Risk Model is a model for vulnerability and assessment of coastal infrastructure. He's on. Okay, Kirk, you can go ahead and take it away.
Yeah, great. Thank you. I just need screen sharing ability if that's possible. So I can share my screen. I'll start out by apologizing to everybody there. My full intention was to be there in person, but I was diagnosed COVID positive on Monday night. So assumed for my own benefit and for more importantly, all your benefits that I probably shouldn't be there in person. So that being said, happy to still provide this presentation remotely, although a bit awkward to do so. So I just need the ability to share my screen for my presentation unless it's up there.
You should be good now, Kirk.
Okay, can I just get one quick verbal cue that you guys can see my screen okay?
Yeah, it's all good.
All right, awesome. So I was here at the last annual conference and talked a lot about our coastal flood risk modeling work that we had completed for Massachusetts, and then also that we were currently undertaking for New Hampshire and Maine. Initially, I was going to give an update on that, but Maine specifically, we've been kind of in a holding pattern waiting for new NOAA LIDAR data, which we just are starting to get rolled in now. So that model is just in the initial phases of process. But also, I thought it'd be worth to, one, just give you a refresher on what we talked about last time, but two, dive into a little bit more about fluvial and pluvial flood risk as well. 10% less than 10% of the area in the U.S. is coastal. And so that leaves a lot of areas that still experience potential flooding issues and risk related to changing climate conditions than just the coast. So that was something we were trying to attack. So recall what really spurred a lot of this on, at least for the Northeast area, was Sandy that had come up, Superstorm Sandy, significantly impacted, New Jersey, New York area. And there was a real heightened focus on what risks might really exist over time, especially due to coastal storm events. That coupled with, projected sea level rise conditions really started to heighten people's concern about critical infrastructure and what might be happening. And a lot of the information that was currently out there and available, and this is just a downtown Boston map from NOAA's sea level rise viewer, are these NOAA and other entities sea level rise viewers, which just basically add water level due to sea level rise, and then you can add a storm surge on top of that. It's kind of a bathtub type approach to flooding. So essentially flat water surface elevation. And if your land is lower than that, you flood the area. And if you understand how coastal storms work, you really aren't dealing with flat water surface elevation. It's much more drastic than that, with waves and winds and velocities and storms moving all over the place. And so this really wasn't adequate enough when we started looking at critical transportation infrastructure, and this started with the central artery tunnel system in Boston. And so this is NOAA's sea level rise view. If you just say, well, let's add 5 feet, which might be 2 feet of sea level rise and maybe 3 foot of storm surge, and this is what floods. And you can see the green areas that don't really connect with the water, but they're lower than the elevation. And so a good first order estimate, but not really what you might need to see, especially when you think about the dynamics of the movement of coastal water. Just to illustrate that a bit further, here's another bathtub approach to the Boston area. This is the water surface elevation peak that you would see. So it's a flat water surface elevation at elevation 12 across Boston. Again, sea level rise and surge that would bring it up to this level. And again, it's just as flooded. Hey, if water can get there, it's going to flood there. But if you look at it, that same storm level dynamically, you get a drastically different picture of what's flooding. You can see the red areas down to the south. You have much higher water levels, about 2 feet higher than the bathtub type approach, because winds and waves drive water down into that southern area. And you can see there's a lot of dry areas if I go back around Cambridge, because there's dams and other things and infrastructure that exists. And there's a much more variability in the water surface elevation due to the way that the winds, waves, and water actually moves. Right, so we developed a high resolution probabilistic modeling to tackle this that we completed from Mass. We've done some in Florida. New Hampshire and Maine, as I mentioned, are underway. And really what that tries to do is look at the physical movement of water. And it brings into play sea level rise, but also tropical and extratropical storms, how those change under changing climate conditions. We use 4 to 5 different global climate models to look at that. And so we get much more information than just a map of where water might be. And we get, the probability of that, the depth, the duration, volumes, pathways, winds, waves, currents, all this information that we talked about during the last meeting. And what really sets this approach apart is a number of things, but it's very high resolution. So we're looking at overland resolutions of 3 to 7 meters. We have an unstructured grid. It's all physics-based. So we're really looking at the hydrodynamic movement of the water. It's not just this flat bathtub. It takes into consideration the waves coupled with the hydrodynamics, simulates all that physical flow of the water, includes dynamic run-up and overtopping of waves. We integrate that structural element. So dams with pumps and sluices, culverts, major coastal structures are all integrated into that model. As I mentioned, we have a changing climate condition. So that means the intensity and frequency of tropical cyclones are evolving as the climate is changing and as the ocean is projected to warm. Everything is calibrated and validated. It was a very peer-reviewed process. And I think the biggest difference that we apply here is this probabilistic approach. So we're simulating thousands of storm events in a Monte Carlo approach, randomly selected. And that allows us to not worry about joint probabilities, like what the tide is doing at the same time the storm is coming in, what, might be happening in that particular case. So we just simulate tens of thousands of events to basically get the full probabilistic distribution of flooding. And what that really leads to is, a little bit different type of map than just a map of, are you wet or not? We get what we call these annual exceedance probability, or in this case, coastal flood exceedance probability maps. And we can look at spatially how the risk changes for various areas. So for example, in this East Boston location here, you can see flooding goes from 20%, which is a once every 5-year type condition, to this 1%, which is once every 100-year type condition. And you can see that's really different than, say, maybe where the pink is, which is once every 1,000 year. And so this is for present day, but you could compare spatially looking at various assets. And in this case, for the central artery tunnel system and all its components, where things were at higher risk than others. so that spatially you can provide prioritization for where your adaptations or where your focus might need to take place. Not only can you think about that spatially, but you can also then do that through time. So this is, for example, what the 2030 conditions would look like. And so now you went from that same East Boston area where you were at that 1% probability. Now you're up to 5%. So that once every 20-year type condition now. So that evolving risk, both spatially and temporally, you can start to assess. And if you really go forward in time, this is like the 2070 type condition in this area. That same East Boston location would give you 50%. So every other year, that particular area would be expected to get wet. And this probability level is just any level of wetness, if water can get there. We can then, of course, pull out things like water surface elevation, depths, waves, and we've produced all these data sets for the state of Massachusetts, and that can be used for resiliency markers. That's what we're doing for New Hampshire. That's what we're doing for Maine to provide that information. So that's coastal-based flood risk, and that whole approach was highlighted in the HEC 25 Federal Highway Administration work, that third edition of the Highways in the Coastal Environment. That approach that we developed was a comprehensive level 3 approach and really is highlighted there specifically for that Massachusetts, Boston area, which we are now extending to other states. However, as I mentioned, there's a lot more flooding that occurs, I'll let this run a second, than just coastal areas. So inland areas and precipitation clearly have a big role in what's happening in a lot of other locations. Here's a couple of videos from places in Maine. Some of you are very familiar with this, but there's a lot of urban-based flooding that occurs. Some of those pictures in the center, and then transportation infrastructure is at the critical center point of a lot of this. And in many cases, for these non-coastal areas, both fluvial and pluvial flood risk areas, there's concern about there's so many of them. Where do I start? How do I prioritize that? So what we wanted to do was bring our coastal-based approach also to inland areas. That included both urban environments and rural environments. We have a number of projects ongoing with right now. I'm highlighting one in Salem, Massachusetts, which is a complicated coastal-based environment because it involves coastal pluvial mix. But we have ones going on in Western Mass, which are very mountainous. The Nashua River through Fitchburg is a location we're doing right now. It has, watershed-based influences with that precipitation-based influences changing over time that influence the flooding risk in that area. So the real key to this approach, again, is that ability to prioritize actions and focus on where is your best bang for your buck. When do you need to take action, and where in other locations can you wait? So this example in Salem, Massachusetts, here is a small area. You can see it on the waterfront here. It is heavily influenced by rainfall events. They have kind of an old and undersized stormwater piped infrastructure system, which you can see here on the right-hand side with the green lines are the pipes, and then the manholes and catch basins that exist throughout the area. They have outfalls that go right out into the Salem Harbor and some of the connecting water bodies, including the South River here. And so we wanted to capture that same probabilistic risk due to stormwater coupled with the coastal influences in this area. And we did that by developing a very high resolution model, even higher resolution than the coastal base. We're looking at, 2 square foot type element areas with about a 15 square foot average. So we can look at flow going down streets and around buildings and all those types of things when we look at rain in this area. And so this is the grid of that watershed area for this particular setting. A couple of interesting things we noticed right off the bat. They had specific piped infrastructure elements that were basically a circuit or a loop that went from one outfall to another outfall. One had a tide gate on it. The other was just completely open, but the water would literally just circulate through that entire piped infrastructure. And so this real quick animation is just what's happening underground for that particular case. And so this is not rain. This is just the tide level going up, which goes up to about 6 feet, NAVD 88, shown here on the figure. And you can see what happens to this part of the circuit. So, the ground elevation is shown, but the entire pipe system basically gets filled with seawater. It can only come in one way, and then when the tide drops, it can go out the other way. But you can imagine what would happen if then you have rain on top of this. You're already during a high tide condition, your whole pipe system is already filled up and the water can't go anywhere. And we found a number of these interesting locations where they even had tide gates on, or even if they didn't, right, when it rained a little bit, the water just couldn't get out. And so here's another portion of the system where it was flooding in an area overland simply because the pipe was full of seawater and really the precipitation had nowhere to go. And so similar to the coastal-based model, what we're really looking at physics-based movement here. So we have a full 2D surface grid along with the piped infrastructure. So we're actually watching where water falls on the watershed. It's a rain on grid approach. So the water actually has to flow to the catch basins. We do not use a sub-catchment based approach where we're shoving water in based on a specific storm event to the catch basins. We're actually letting the water physically move throughout the system and rain on the area. The buildings aren't included. If there's stormwater drains off the buildings, those are included. But it basically represents that physical movement of water. And then what we want to do is integrate that probabilistic approach. So this gets fairly complicated, especially when you start thinking about precipitation events. I included this one figure in here, the typical SES type 3 design condition for a 10-year, 24-hour event, which is what this rainfall intensity is here. And that tries to capture what, kind of a very intense rain event is. What we end up doing is taking the NOAA Atlas 14 data, which is site-specific, developed for various regional areas. And we basically model every single recurrence interval that occurs from 15 minutes down to 10 days from the 1 year to 1,000-year condition. So we're looking at a full range of storm conditions, not just one design level storm event. Then we use Huff curves to not only to figure out what the total magnitude of the precipitation was, but also the precipitation temporal distribution. So that can be in the first quartile, the second quartile, the third quartile, fourth quartile. If you're not familiar with these Huff curves, what they are, they're based on actual storm events that have occurred in those distributions. So we not only simulate every single type of return period and magnitude that occurs, but also every single temporal distribution in terms of the intensity and when that occurs over a certain time period. So for example, with a 96-hour, 100-year precipitation event, we simulate another 40 of those basically to get that temporal distribution of the rainfall. We then also have to think about things like how it's phased with the tides, especially for short-term events. Obviously, a 10-day rainfall event doesn't really matter what the tide is doing so much. But for, say, a 3-hour event, it matters if the tide is low when it starts or high. So we did a comparison between phasing of the tides when the rain starts versus what the tide is doing. And you can see, unless you have very small return periods like the 1 year or 2 year event, all the other events have very different phasing considerations. So not to make our lives more complicated, but we also had to add phasing of the tides relative to the rainfall event. Really what this means at the end of the day is we're literally simulating well over 20,000 conditions of rainfall. We're able to do that because we have the HPC and computer capacity to really handle those types of runs. And you can see, when you think about a 96, 100-year storm event, for example, a 96-hour, 100-year storm event, how that rain falls really makes a difference in what is occurring on the ground. So on the left-hand side, this is the depth of flooding you would see over, a very small amount. This is the maximum or peak. And you can see very quick, a lot of the rain falls up front in the 96 hours is completely different than if a lot of it falls in Q3 over a 50% average. You get a drastically different picture of flooding. So that's why we have to simulate all these different conditions. And then we're able to take all those events, put those into this annual exceedance probability again, and we can look at how that changes spatially and then temporally using increased precipitation extractions from people like Cornell that have done this work to say how the precipitation amounts are changing over time and really start to compare, given different depth thresholds, what the rainfall flooding looks like and where your higher risk probabilities are. So for example, this park has a certain level of 20% probability now, but as you go forward to 2050, that increases to almost 100%. Every time it rains, it's going to flood in that location. Just another quick look at that. Here's what it looks like. This is, again, is over 9 inches of flood depth that might occur. So this is present day. Have some pretty significant problems in areas. And then if you jump to 2050, you start to see where those problems really lie. So you get that same feel and look as you get from the coastal model with the pluvial fluvial approach. And then in this case, it's actually directly integrated to the coastal model and what's happening in the coast. So what does that mean at the end of the day? Well, we think it's a pretty significant improvement over the catchment-based approach where you're just looking at one design storm, which doesn't really tell you where to prioritize your actions. Again, it's a fully physics-based water movement. We have the rain on grid approach, very high resolution. We get that full distribution of storms. So we can pull out individual storm events as well. So if you want to look at it, just the 10-year type conditions over 24 hours, you can look at just those. If you want to look at 100-year conditions, you can look at those. If you want to look at the full distribution, that's what I was just showing you. We can combine that fluvial, pluvial, and piped infrastructure. So we have both the surface and the subsurface involved, as well as the coastal. We're looking at evaluation of both present day and future conditions. And then some of these figures I'm showing here are looking at the impacts of proposed solutions. So the Salem project advanced once they had all those model results. They targeted a key location, which is shown here, for an adaptation where they're putting in a berm structure. They're doing a new waterfront, looking at how that protects not only from coastal storm events, but also if you block stormwater from flowing out, what is the rainfall events and how does that work? The last thing we're working on is the scalability of it all. This is a pretty pilot-based project here. Like I said, we're doing Fitchburg right now, which is a much larger area. What we'd really love to do is get this to state level, similar to what we did the coastal standpoint of things, and then integrate that all together. And the idea here is it's a standardized data set, gives you that probabilistic risk. So if you're working on, culverts and bridge crossings across the entire state of Vermont, for example, where there's many, many problems, you could identify and prioritize where the actions really need to take place because you can look at both spatial and temporal change over time. Thank you.